Some circuits are wired in such a way that you can't use the series and parallel equations alone to figure out the different currents in the different parts of the circuit. So to deal with these more complicated circuits, you have to use Kirchhoff's rules. So there's Kirchhoff's junction rule and Kirchhoff's loop rule. The junction rule says that at any junction point in a circuit, which is the point where like wires come together, the sum of all the currents going in must equal the sum of all the currents coming out. And since currents are composed of charges, that's because it's based on the law of conservation of electric charge. You can't create or destroy charges, they have to go somewhere. So all the currents going into the junction have to equal all the currents coming out of the junction. The other Kirchhoff rule is the loop rule, which says that the sum of the voltage increases and decreases around any closed loop of a circuit must be 0. So when you're going around the loop one time, you're going to go up in voltage across like batteries and things, and you're going to go down in voltage when you cross resistors. It all cancels out to become 0. And that's based on the conservation of energy. So in example 1512, we're going to refer back to the circuits in example 15.6. So if you want to take a look back at that page, that was the one where you had a 10 ohm, a 20 ohm, and a 60 ohm resistor, and you had to connect them first in series and then in parallel. So the first one was in series, and the circuit looked something like this. It just had the battery and then the 3 resistors, which looped back to the battery. The battery was 12 volts, and the 3 resistors were the 10 ohms, the 20 ohms, and the 60 ohms. And we already figured out everything about the currents and different things. We even got the voltage across each of those 3 resistors. So if you just want to show that Kirchhoff's loop rule holds for this series circuit, you just start at a certain point in the loop. This is one single loop, so let's just say we're going to start at this point down here and make one complete loop around the circuit to back where we started. Well, the first thing you cross as you're making this loop is 12 volts, so that's an increase in voltage of 12. So we can start by just writing actually I'll put it as an equation first. We can start just by writing V for the battery, and then we're going to go across these 3 resistors, and we're losing a little bit of voltage for each one that we cross. So if you look back on on that first page, across the 10 ohm resistor, there was 1.33 volts, but I'm just going to call it for right now minus I, the current, times R1, minus, for the second resistor, it was the current times R2, minus the third resistor, which is the current times R3, and then there's nothing else after that third one, it just goes right back down to where we started. So we want to add all these together. So the voltage was 12, minus the current times the first resistance, we just said was the 1.33 volts, minus the current times the second resistance, the voltage across that one was 2.67, and minus the current times the third resistance, which was 8.0. When you add all those together, it comes out to be 0. So we've just established that Kirchhoff's loop rule holds for that series circuit. And part B is to show that the junction rule holds for the parallel circuit. So you remember what that one looked like. It was the 12 volt battery, and then you've got the 3 resistors coming off it, and they connect together and go back to join the battery. So the junction rule would take place either right here or right here. And you remember there is 2 amps coming off the battery, and then the remaining 3 through each of those 3 resistors. One of them had 1.2 amps going through it, another one had 0.6 amps going through it, and the third one had 0.2 amps going through it. And when you add those together, you get 2 amps, which is how much current was going into that junction, because that's going into this point right here. For example, 1514, you have this circuit right here, and you just want to determine what is the resistance R in this circuit. And you're given these two currents coming into a junction. So that should be pretty obvious what the first thing to do is. We can just start with Kirchhoff's junction rule, which I'll just abbreviate KJR. The two currents going into that junction, which is this point right here, have to equal the currents going out. So 1 amp and 2 amps coming in means that 3 amps is going to be coming out of the only remaining branch. So just to get that written down, just say 1 plus 2 equals the 3 amps, and that's going through resistor R. But we're actually asked to figure out what is that resistance R, and the way we're going to do that is we can now do the Kirchhoff's loop rule, KLR. There's 3 loops in this circuit. A loop is just a complete closed area, so starting from this point right here, we could say this is one full loop, or we could say this is one full loop, or we could look at the outside and say this whole thing around the edge is one full loop. Well, going around the whole outside edge isn't really going to help because it doesn't take us through this resistor that we're trying to figure out. So for this one, you can either focus on this loop right here, or you can focus on this loop right here, because both of them will eventually pass through R. And it doesn't matter which one you look at, you get the same answer either way. So I'm just going to focus on this closed loop right here. I'm going to start at this point that I'm going to mark with the X, and I'm going to go one full time around that loop back to where I started. I'm going to add up all the voltage increases and voltage drops. So the first thing you do is, as you're going around, is you go across the battery. Every time you go from the negative side to the positive side, there's a voltage increase. So you just put down, you start off with a positive 16, and then every time you go across the resistor in a direction of current, that's a voltage drop. So I'm going across this resistor. There's a current of 1 amp in this segment, so 1 amp current times resistance, 1 amp times 4 ohms will give the voltage, so 1 times 4 is your first voltage drop. Then as you keep on going, you pass through this other resistor, and that's going to be current of 3 times that resistance. So it's going to be minus 3 times R, and then that takes us right back to where we started. And we know that in a closed loop, it has to equal 0. Now we can just solve this equation for R. We have 16 minus 4 is 12. Bring the 3R to this side. So our first step is to have 12 equal to 3R, which makes 3, which means you can just write down that R is equal to 4 ohms. So for this last Kirchhoff's problem, example 1514, you're told that the current shown in this circuit is equal to 2 amps, and you want to determine this resistance R. Well, the first thing to note in this circuit is that it has 2 batteries in it, 12 volts and 6 volts, but they're actually facing in opposite directions, so they're not going to add together, because on this one, you've got the plus terminal over on this side, implying the current will come out this way, but on this one, you've got the plus terminal on this side, implying that the current would come out that way. Well, the current can only go in one direction in the circuit, so it's basically the bigger one's going to win. So the current is going to go clockwise around the circuit. So if you want to just go ahead and draw that on there, so we can say that this is one full time. So we're going to start with the loop rule, because there are no junctions in this circuit. You only have junctions when you have things in parallel, like in the circuit we just did in the previous example. So this one is just one single loop, so we're going to use the Kirchhoff's loop rule. So we're going to say we have to pick a starting point. I'm going to pick the starting point right behind that 12 volt battery. So I'm going to put a little X right there. That's where I'm going to start. So my first thing is going to be the voltage increase going across that battery, which is 12. And then, as I go across the other battery, which is the next thing in line, that's going to be a 6 volt decrease since it's pointing in the opposite direction. So minus 6. And then it's going to take me through 4 resistors. I've got the 0.2, the R, the 1.5, and the 0.3. And it's the same current through all 4 of those resistors. So what I can do is, to get the voltage drop across each one, which is current times resistance, since the current is the same for all 4 of them, I can just go ahead and factor it out. So it's going to look like minus the current, which is 2 times, and the 4 resistors are 0.2, then R is next, and then 1.5, and then 0.3, and that takes you right back to where you started at this point right here. So the loop rule says that all of that has to equal to 0. So if you solve this equation, you end up getting, overall, you're going to end up getting, I'm not going to sit here and go through all the steps, but you do get the R is equal to 1 ohm, if you want to go through and kind of figure out the math on that on your own. So that's the value of the resistor. So that was part A. For part B, you want to figure out what is the potential difference between point X and point Y. So what is the voltage drop as you go from this point to this point? And you can go either way around the circuit, it doesn't really matter. So I can go from that side around to there, or I can go from this side around to here. So I'm just going to pick the right side. So I'm going across this battery, which is a drop of 6. So we start with the minus 6. And then we go across that resistor, which is minus 2 times 0.2. So again, we're looking at voltage, minus, and then the voltage drop across that next resistor, which we figured out is 1. So it's going to be minus the current 2 times the resistance of 1. And all that will give you the voltage drop going from X to Y, which turns out to be negative 8.4 volts. The negative is not really important in this case. All that matters is you have the number of a voltage, the potential difference of 8.4 volts. And for part C, how much energy is dissipated by the 1.5 ohm resistor in 1 minute? So energy, remember power is energy over time, so you can say that energy is equal to power times time. So let's figure out what is the power in that resistor. Well, remember there was 3 different equations for power. You could say P is equal to I times V, or you could say, if you substitute in Ohm's law, you could say it was I squared R, or you could say it's V squared divided by R, depending on what you know. Well, in this case, we know the value of the resistor, the R. We also know the current through that resistor, so let's just go ahead and use the one that has current and resistance, which is I squared R. So we can just plug that into this equation for the P. So energy will be equal to I squared R, and then times this T. The I squared R, the current was 2, squared, times the R, which is 1.5, times the T, which is 1 minute, which you've got to convert into standard units, so that's 60 seconds. And so you have 2 squared times, which is 4, times 1.5 is 6, and 6 times 60 gives you a total answer of 360 joules.